All right, so let's get started. I want to thank everyone for joining us today. Good afternoon to many of you, good morning to some of you, and I believe we even have some international folks, so good evening to you over there across the sea. Very cool. So first of all, we've got the chat and the Q&A open, so if you have any questions at any time, I've got everyone here muted except us, obviously, while we small chat beforehand, but you can ask any questions throughout. And also, normally I ask if people can hear me, okay, but since you could apparently hear us before we even started, I'm going to take that as a yes. But yeah, go ahead and ask some questions throughout, and when we're all done here, I'll tackle as many as possible before time starts running out. So today we're going to get back into the wonderful world of heat pipes and not just focus on the wraparound heat pipe. If those who have been with us on earlier sessions, we focused on the heat recovery modules and then our DHPs, or our dehumidification or wraparound heat pipes. But today we're actually going to take it a step further and focus on dedicated outside air systems. So dedicated outside air systems, or DOAS as it's commonly referred, I'm going to just focus on what that actually is and discuss the pros and cons of that type of system versus your more conventional mixed air type system. And then of course, what's a heat pipe? I'm sure everyone here is very familiar at this point on what a heat pipe is and how it works, so we'll just make it a quick refresher for most of you. Though it could be more of a tutorial for some, but we'll get that covered. But more importantly, how do heat pipes work hand in hand with your DOAS equipment to optimize that system? And we're also not just going to look at that, but Standard 920 is brand new, just came out this year, and it's solely focused on DOAS equipment. So I want to introduce 920 to you. It's going to be implemented into 90.1 soon, so it's a good one to know, and it introduces not so much a new metric, but a new standardized metric called MRE. So here's an example of your conventional mixed air system. This one's using VAV boxes. It's also using chilled water. It could be DX. But the bottom line here, if we're talking mixed air, then the return air and the outside air is being mixed upstream of the coolant coil. So the coolant coil is seeing that mixed air, ventilation and return, and dehumidifying it as a whole, and then delivering that air out to the space where some kind of air terminal unit, in this case a VAV box, is going to deliver that air to each zone and then reheat it or vary the volume as necessary depending on the load in the space. Pretty common. Downside here, one is that you know, you got to add the reheat to make it comfortable out there, but reheat is not cheap. You do have to pay for it, and unfortunately hot water loops are not very efficient. I mean, your typical boiler or your hot water loop is going to have a COP of about 0.5, meaning that for about every unit of energy you're using to get that hot water, you only get about half of that out of it. And if you're using electric heat for that reheat, it's even less efficient. So it does cost you some money. Also, those VAV boxes, because they're delivering a combination of outside and return air, they won't close completely. They're always going to be delivering air to the space, and you always got to make sure you're having enough ventilation air out to the space, and that's a result of that air being combined. You've got better be safe than sorry, and make sure you deliver some ventilation air out into the space. So here, conversely, is the decoupled dedicated outside air system. Decoupled because now, instead of mixing the outside air with the return air upstream of one coolant coil, you're actually separating or decoupling the two. So you have an air handler or a DOAS unit that is strictly handling ventilation air. Then you have separate air handlers for recirculation or handling all return air. Now, whether we're talking DX or chill water, air-cooled, water-cooled, it could be anything serving that DOAS unit, or even the recirculation units. They're each doing their own thing. The recirculation is focused solely on sensible load. There is obviously some humidity and some moisture in the return air, but it's minimal compared to all the heat, the sensible heat that's coming back. So the recirculation units are just worried about the temperature, while the DOAS unit is worried about ventilation and humidity control. And if it is a DX unit, then you get the benefit of free hot gas reheat. So now that whole half COP hot water loop, or even worse, electric heat, a lot of that gets eliminated because you can get free hot gas right from the DOAS unit. Another benefit is those VAV boxes can now close completely because you're not worried about not delivering enough ventilation air. It's being handled by its own DOAS unit. So you can close those completely, and that allows you to not what they call over-air the system. You're truly monitoring the amount of outside air that's needed and just adding the recirculation air as needed to control the temperature out in the space. And when you're not having to cool more outside air than is unnecessarily needed, you're able to reduce your cooling load by quite a bit. So whether we're talking the chiller, the cooling tower, the pump, everything gets reduced. And you generally find that in the summertime that energy is able to get reduced by up to 40%, which is quite a hefty number. And I do want to point out that that supply air, or the air coming out of the DOAS unit, and here, right there it is showing it being delivered out into the zone. But it could be done many ways. It could go directly to the space. It could go back into the inlet of the air handler like was shown before, except now it's been pre-treated. It could go being fed to the mechanical room as a plenum and then being drawn from by each air handler as needed. A lot of times you see decoupled systems serving primary air to chilled beams as well. So there's a lot of uses and a lot of ways, like any system, that a dedicated outside air system can be designed. So we're going to talk about the advantages. I'm completely skipping the cons because really the only con to a dedicated outside air system is that it costs more money. But like with anything, there's a difference between price and value. And if you're willing to pay a little bit more up front to save a lot more down the road, then there's lots of benefits to be had. So one, obviously, we touched on is over-airing the space. I mean, again, if the DOAS unit is strictly handling ventilation air, then you don't have to worry about providing too much ventilation air out to the space. It's taking all that for you. So you're not providing too much air, which is unwanted, unnecessary energy. So whether we're talking about a ventilation rate that you're trying to meet or an air change requirement, it's strictly focused on giving you what you need and nothing more. You also get some nice occupancy control out of it, whether we're talking occupied versus unoccupied, or a demand control ventilation system where CO2 sensors are estimating the amount of people out in the space. It gives you a lot better control from an occupancy standpoint to reduce the amount of ventilation air going to the space. You obviously get better humidity control. Instead of one mixed air coil doing everything, you've got one coil solely committed to drying out the outside air, which is where the bulk of that humidity is coming from. And that's going to lead to better indoor air quality. Less threat of moisture being in the space means less threat of mold and mildew being out in the space, and that's obviously a good thing. It does enhance the opportunity for energy recovery if you're bringing all the outside air to a single point. It makes that a lot easier, gives you a lot better options. And it also gives you more accurate building pressurization. Again, it's all in one place and more accurately measuring what's coming in versus what's coming out. And you do get more efficient economizer control. Again, if you're able to use that outside air for economizer mode and it's all right there in one source instead of mixing, makes it a lot easier and a lot more efficient to control that. And oftentimes when it comes to lead, you do find that there's an easier path to get more points simply by decoupling that system. So many advantages to a DOAS system, and I haven't even gotten into the heat pipe portion. So quite the segue there. Let's talk about heat pipes. And again, I'm assuming everybody here is familiar with the next 2 or 3 slides I'm going to show, but again, better safe than sorry. So here's your traditional heat pipe. It doesn't require any power. It just requires a delta T, and that delta T is going to make it work. And basically, you put this tube with refrigerant in it, and you apply heat to one side. That refrigerant is going to pick up the heat. That refrigerant is going to boil. It's going to go to the open area, which is the other end, which is now cooler. It's going to give off that heat, condense back to a liquid, and it's just going to keep going back and forth, phase changing and transferring heat from one end to the other. Again, with no power, no moving parts necessary. So we have at HPT have actually taken this one step further and developed what we call the loop circuit. So instead of one single tube with all the liquid and vapor going back and forth within the same diameter, we actually have more of a loop type circuit where the vapor and liquid is somewhat chasing itself in kind of a racetrack mode. So if you're looking at this picture and let's say the airflow is going in and out of your computer screen, if you didn't have any air or it was the same temperature, you would just have some liquid refrigerant sitting at the bottom of that loop. All of a sudden you apply warmer air, in this case to the right side. That refrigerant on that side is going to pick up the heat, boil, go up that loop, travel to the other end, give off the heat, condense back to a liquid, and keep going, in this case, in a counterclockwise type loop. And if it's energy recovery and the season changes and that hot outside air turns to cold outside air, then that refrigerant is just going to change directions all by itself, no tilting required, and just keep doing this loop type circuit as long as there's airflow and as long as there's a delta T. So for the wraparound heat pipe, we've taken it another step further, and instead of simply going in a loop from one airstream to the other, we're using it in a single airstream. And now when you got this hot air coming in and the refrigerant picks up that heat and boils, instead of that refrigerant vapor going to another airstream and simply dumping off the heat, it's now wrapping around the coolant coil and we're using it as reheat. And like we just discussed, you know, it's not just, when it comes to air conditioning, you're not just controlling temperature, but you're controlling humidity as well. And one way to do that is to overcool and then reheat as needed so you don't freeze everybody. And like we were talking about, that reheat is not cheap, so being able to get the free reheat through the wraparound heat pipe is a bonus. So if we look at that same circuit on your site chart here, you can see that if we didn't have a heat pipe on it and you had 80-degree air coming in and you had to get 50 degrees off the cooling coil, you'd have to have enough cooling capacity to go from point A all the way down to point C. But if you put a wraparound heat pipe on it, then now we're doing some pre-cooling for you. So now we're going to cool down from A to B. So now that cooling coil, instead of seeing 80-degree condition A, is going to see 70-degree condition B, and you don't need as much cooling capacity to get down to that 50-degree dew point now. And then, of course, whatever that pre-cool heat is just being wrapped around and being used as the free reheat from C to D. So for dedicated outside air systems, if it's DX, then of course that reheat is free anyway. You can use hot gas reheat, get you some free reheat, and everybody's happy. That's a big chunk of savings right there. But the downside is that it's just waste heat. I mean, I don't want to downplay free heat because that's awesome, but it is just waste heat. When you compare it to the wraparound heat pipe, you're not just getting free reheat, but you're getting free cooling as well. It's really the only device that's going to save you on both the upstream side and the downstream side of the cooling coil. So you're going to get twice as much BTU savings with a wraparound heat pipe as you would with hot gas reheat. And not just that, that pre-cooling has allowed you to reduce the capacity of your cooling coil. And what I want to show you here is that you're not just able to reduce the capacity of your DOAS equipment, but you can make that net equipment, let's say, that packaged equipment, more efficient from an EER standpoint. So let's take a look here. This is a 25-ton nominal tons DOAS unit. In this case, let's say it doesn't have a heat pipe on it. It's going down to a 52-degree dew point, so the EER for that 25-ton unit is 11.7. Well, now let's say, again, we've done 5 tons of pre-cooling. So to get 25 tons of net cooling, you only need now a 20-ton DOAS unit. We're accomplishing 5, it's accomplishing 20, you're getting 25 tons of cooling. The one before has got hot gas reheat. We're providing free reheat on the wraparound side. We're getting the same dew point, but now not only have we reduced your capacity obviously by 20%, so we've made the unit smaller, it's going to weigh less, but more importantly, it's going to be more efficient. And you can see right there we increased that efficiency by about 25% because it takes a lot less energy to overcome the little bit of static pressure that we add to the system. So basically a heat pipe, no moving parts, requires a little bit more fan energy. So that brake horsepower is going to bump up just a hair, while the 25-ton system needs 5 tons of compressor power, and that takes a lot more power draw. So to get the same capacity, we're going to get ours a lot more efficiently. And the other bonus here is it may not cost you anything. To go down from 25 tons to 20 tons, yes, the heat pipe costs money, but you save money right off the bat by downsizing your system. So keep in mind that you can get a wraparound heat pipe, and I'm not going to say this is every time. It depends on the project. It depends on the manufacturer, but there's a very good chance that the add for the heat pipe is about the same as the savings for downsizing the equipment. If it's not the same, it's pretty darn close, and you've just made your system about 25% more efficient. Another nice thing is that it's going to meet code. So 90.1, most state building codes are based on some version of 90.1. You know, every 3 years they update it, but all of those are telling you that depending on what climate zone you're in North America, it gives you a nice chart and tells you that if you have this much outside air and this percentage of your supply air is outside air, then you have to have energy recovery. And not just any old energy recovery. It has to be energy recovery that's at least 50% enthalpic effective. There's also some exceptions to that rule. You know, labs, kitchens, they have their own exceptions, some other stuff, but the one I want to point out is that the last exception listed is that if a wraparound heat pipe is being used, now AHRI calls it in-series heat recovery, but that's because it's all happening within the same airstream as opposed to 2 separate airstreams. But if you're using in-series heat recovery or a wraparound heat pipe, then you have met code. You do not have to do anything else. So know that if you've got a DOAS unit, single path, with a wraparound heat pipe in it, and you put it in there to downsize your equipment and make it more efficient, you have met code. You do not have to do anything else from an energy recovery standpoint to meet code. It has now been met. So let's talk standard 920. This is new. So 920 came out this summer sometime. It's been being worked on for several years. But more importantly, standard 920 is now leading to 90.1's adoption of it next year, and I'm being told as early as January. So what does that mean? Well, up to this point, DOAS equipment, like all other cooling equipment, the only way to rate efficiency has been through EER, or a version of kW per ton. But big difference between DOAS equipment and other cooling equipment is where chillers and stuff like that, the main focus is reducing load or cooling a load. The main purpose of the DOAS unit is controlling humidity or removing moisture. So 920 sets a standard on a new metric they call MRE. And EER is going to go away as far as a measuring point for DOAS unit, and from now on it's going to be focused on MRE. So what is MRE? Excellent question. MRE is your moisture removal efficiency. So there is no longer, I don't want to say no longer a concern with EER, but it's not going to be how DOAS equipment is measured or standardized moving forward. It's all going to be based on how much moisture is being removed. So we're talking MRC, or moisture removal capacity, or pounds of water per hour that DOAS unit is able to remove. But MRE takes it one step further and doesn't just look at how much is being removed, but how efficiently is it removing it. So every DOAS unit is going to have an MRC, or a moisture removal capacity, and tell you how much pounds per water based on how many grains are coming in versus how many grains have been removed by the system. But more importantly, how efficiently it's doing it. And that KW draw is based on compressors, fans, static pressure, and even if there's supplemental heat like hot gas or hot water, all of that gets included to figure out how much power is needed for this DOAS unit to remove so much moisture. So MRE is not just now standardized by 920, but 90.1 is going to set up some minimum tables that all DOAS manufacturers are going to have to comply with, and all DOAS manufacturers are going to have to start publishing their MRE at standard operating conditions, which I'll show you. But not just MRE, but there's another term called ISMRE, or the Integrated Seasonal MRE, which is very similar to like the NPLV of a chiller, where if MRE is at full load, ISMRE is measuring the part load performance, let's say. So it's a weighted MRE looking at various conditions, and you can see them below, conditions A through D, where A is full load or at 95, 78, all the way down to 60 degrees, and it weights those and tells you what your average, let's say, MRE is going to be based on a standard operating conditions. It also is assuming that the return air is coming back at 75 degrees and 50%, and that the supply air is going to come off the coil at a maximum dew point of 55 degrees and warmed up to 70 degrees. So whatever supplemental heat is needed to get it up to 70, that is going to be factored in to tell you what your MRE is going to be, or as well as your ISMRE. So as you can see here, it is more important than ever to not just dehumidify the air to make it comfortable and get rid of mold and all that nasty stuff, but to do so efficiently. Fortunately, we are now living in a world where saving money and reducing energy is more of a focus than ever before, and converting DOAS from an EER-based system to an MRE-based system will put even more of a focus on that, which is awesome news. But let's talk about how the heat pipe can be used to not just improve the EER, like we were just talking about, but now the MRE. I mean, EER, that's so 2015. Let's be serious. So let's talk about MRE. That's the future. So let's take that same 25-ton DOAS unit that didn't have a heat pipe in it. For it to get down to a 52-degree dew point, it had to remove about 162 pounds per hour of moisture. And to do so, it took about 29 kilowatts of power. So your MRE, again, is your moisture removal capacity divided by those KWs. So you get an MRE of 5.6. Now, we were able to not just use a 25-ton unit, but use a 20-ton unit where we're doing 5 tons of pre-cooling to get you a net 25-ton system, still getting down to the 52-degree dew point, which is therefore going to have the same moisture removal capacity of 162. But again, we were doing ours with less power because it takes a lot less power to overcome our little bit of static than it does for that 25-ton system to have 5 extra tons of compressor horsepower doing the same work. So for us, instead of 29 kilowatts, we only need about 23 kilowatts of power, and obviously now our MRE is going to go up. So we're actually able to increase our MRE by about 25 or 24%, which is awesome. So we're already being focused to reduce the MREs, and if you can increase that MRE by 24% simply by adding a wraparound heat pipe, which is going to shrink the system, and let her remind you that it may not even cost you anything because you're shrinking from a 25-ton system to a 20 system. 20-ton system, and it's more efficient across the board, whether you're looking at it from an EER standpoint or the MRE standpoint. Now, another cool thing you can do is not just take the same DOAS unit and get the same total capacity, but let's say we want to dry out the air even further. Let's say that that 25-ton system without the wraparound heat pipe on it can only get down to that 52-degree dew point. Well, now you add a wraparound heat pipe to it. We're going to do some pre-cooling, so that same cooling coil is going to do less sensible cooling, more latent cooling, and drive down that dew point even further. So let's take a look at that same example, but now instead of downsizing the equipment to get the same capacity, we're going to use the same equipment, add a heat pipe to it, so now that coil is able to do more latent cooling and remove even more moisture out of it, drop that dew point down from 52 all the way down to 48 degrees, and it's done so at such little power because, again, all we're doing is adding a little bit of static pressure, so a little bit more brake horsepower for the fan to overcome. And now we've removed about 10% more moisture and improved the MRE by 10%. So you can either downsize the equipment to make it way more efficient, or you can keep the equipment the same size, dry out the air further, and still make it more efficient, which is pretty awesome. So when looking at these wraparound heat pipes, whether you're looking at it from a capacity reduction standpoint, an EER standpoint, an MRE standpoint, and drying it out even further to drop that dew point even further down, there's not many ways to do that while also getting the free reheat from one device, and that's what the wraparound heat pipe is doing for you. So I want to take this even further. At this point, we've talked about how to optimize the dedicated outside our system with a heat pipe. Now let's talk about how to optimize the heat pipe, which of course is going to optimize your system even further. And of course, I'm talking about making it a controllable wraparound heat pipe. So in many cases, the DOAS system is providing neutral air, or let's just say that it doesn't really, I don't want to say it doesn't matter, but that supply air temperature can float because you have some downstream terminal units handling the sensible load. But there are many cases where that temperature does matter. And if there's a downside to the wraparound heat pipe, it's that, it's all driven on delta T. So the warmer the air coming in, the more heat we're going to recover, the more pre-cooling we're going to do, which is great, but the more reheat we're going to provide as well, and that might not be so great. So how do you control the amount of reheat that's being done? You put control valves on the heat pipe. So typically we're going to use 24-volt solenoid valves on the circuits. If we get a large number of circuits, we'll bump that up to 120 volts to keep everything a little bit smaller. And then we stage those valves together, typically 3 or 4 stages, so you get 3 or 4 stages of heat pipe control. And here's one showing for you. So let's say there's 12 solenoid valves there. We wouldn't take the top 3 and make that a single stage, because if you turn that off, now you have warm, humid air coming through the top of the coil and conditioned air coming through the bottom, and that's no good. You don't want to have any stratification like that. So we would actually stagger, let's say there's 4 stages, every 4 valves to be 1 stage, so you're getting a nice consistent temperature gradient coming to your cooling coil. Now, we can, in larger systems where the number of solenoid valves just gets to be ridiculous, we can go to what we call our split passive type wraparound heat pipe, where we've got vertical tubes and common liquid and vapor headers going from pre-cool to reheat. This does allow us to simply use modulating valves in a liquid line, which is going to greatly reduce the number of valves. But it also diminishes performance. Not only are we taking up some face area with those headers from both the top and the bottom of the airstream, but we're also combining multiple circuits into one by using those headers. So you do lose some efficiency. So we're gonna lean towards just your basic solenoid valves as much as possible, unless, again, the number of valves gets too great. But we approach that on a job-by-job basis, so if you have any questions on which way to go, we'll certainly work with you on that. So I want to look at a quick example of why and when to use control valves. So here's an example, 100% outside air, 10,000 CFM. Let's use those standard operating conditions in 95, 78. Let's say it's 50-degree dew point coming off the cooling coil, and let's say that the warmest the air you want to be delivered out to the space is 65 degrees. You don't want it to get any warmer than that. Well, one thing you can simply do is just use a 2-row non-controllable heat pipe. At 95 degrees and 50 degrees off the coil, the most reheat you're going to do is 13.5 degrees, so you're never hitting that 65 degrees. It's never going to get too hot. When you factor in the static pressure hit using typical utility rates, I would budget this at about $1 a CFM, so let's just say it's $10,000. And let's say you're going to save on both the pre-cool and the reheat, accounting for the fan penalty, about $8,200 a year. That payback's just over a year, which is pretty common. Depending on where you're located, what utility rates are, and what kind of application and operating hours you're looking at, it's very common to see 1 to 2 year payback with a wraparound heat pipe. And again, that's because you're not just saving on the pre-cooling side, and you're not just saving on the reheat side, you're saving on both. But the downside here, yes, you don't have to control it. You can let it run, do its own thing all the time, and it's never going to be too hot. But at the very least, even on the hottest day, that's 1.5 degrees that you're missing out on of free reheat. If you can get up to 65, well, every other day it's even worse. But even on that worst day, that's a full 1.5 degrees that you're having to pay for reheat. So what can you do? Well, you make it a larger heat pipe and put control valves on it. Because obviously when you make it larger, now at that design day, you're not just getting 13.5 degrees of reheat, you're getting almost 18 degrees of reheat, and now it's going to be too hot at those hottest days. So that's those days that you would actually shut off the valves, but that's a small window because again, how often are you at design day or design conditions? Core NASH rate's 1%, but let's say it's upwards of 5%. Well, that's still a very small portion of your bin hours that you'll actually have to shut off the circuit. The rest of the time, you've got twice as many rows recovering heat, and that's a lot more heat to recover. So even though we're adding about twice as much static because we've doubled the rows, and it's going to cost quite a bit more. Let's say it costs twice as much to make it 4 rows instead of 2 and add a whole bunch of solenoid valves, but the savings are going to be quite a bit more. I mean, see right off the bat, you're saving an additional over $4,000 a year because you have twice as many rows recovering heat the majority of the time. And you still get a payback of less than 2 years, and once that's paid off after a short 2-year window, you save an additional $4,000 a year. So don't look at the valves as simply a means to control temperature. Look at the valves as a way to optimize the heat pipe, oversize it, so to speak, because again, you don't spend most of your time at 95 degrees or that peak day. You spend most of your time less than that. So why size your heat pipe so that it's doing its best savings at the day you spend the fewest amount of time? Let's size it for the days you're going to spend the most amount of your time and really capture those savings. And we can take it a step further. If, in this case, 50 degrees is coming off the cooling coil, if there's some time in that year where you're going to need 50-degree supply air, well then by all means you need to make it fully controllable, put a valve on every circuit so that you can shut the heat pipe off completely. But let's say that you're always going to want some reheat. Let's say that you'll always want at least 55-degree air coming out of the system. Well then why would you put valves on every circuit? Let's just say we put the valves on half the circuits. So one thing you'll find is that when you do a controllable heat pipe, as soon as you add control valves to it, you do lose some performance because valves are essentially adding friction, so now that energy is not going towards reheat, it's going towards friction loss. So when you add half as many valves, you actually gain some performance. So instead of at design day 17.7 degrees of reheat, we're getting about 19 degrees of reheat. So throughout the year, there's less valves adding friction, so you're getting even better performance. You're adding the same statics, there's still 4 rows, but now there's half as many valves that you're paying for. So you get better performance, you pay less for it, so the payback is even greater. Now you're saving, and I think I said $4,000 before. Before you were saving about $2,000 extra each year after it's been paid off. Now you're saving about $4,000 each year after it's been paid off, and it was just paid off a lot quicker because you didn't have to pay for all those unnecessary valves. So when you get into our selection software, it's easy to pick a non-controllable heat pipe, it's easy to pick a controllable heat pipe, but you do not have the option for a partially controllable heat pipe. That is something we have to do internally. So if you have a job where you know you want control valves, but you know that you'll want some reheat all the time, let us know and we'll work with you to get the right selection to optimize not just your savings up front, but down the road as well. So just to summarize, your decoupled dedicated outside air system, with the exception of it costing more, is widely viewed, and as you saw today, a highly superior system compared to your mixed air systems. Mixed air are nice and easy, they don't cost much, but unfortunately they're not as an efficient way of doing things, and in the world we live in today, we're not just, we were talking about MRE, but just the whole system has to be even more efficient. Decoupling that outside air to let it solely focus on the ventilation air is a highly superior way of doing things. And standard 920, again, it's new, it's here, EER is still around, but it's a thing of the past when it comes to DOAS. Don't be talking EER when it comes to your DOAS units. Talk about MRE. They're all going to be talking about it, publishing it, and there's going to be minimum requirements that I would not be surprised if a handful of the current DOAS equipment manufacturers out there are going to have to figure out make some major improvements to hit these new 90.1 requirements. And of course, how can the heat pipe be used to improve that DOAS system? Whether we're talking reducing capacity, improving EER, or more importantly, improving that MRE. The heat pipe can do it all. And again, if you can do it without paying any extra for it because you've downsized your equipment, well then it's almost a no-brainer. And finally, how do you optimize the heat pipe? You do it with control valves. And again, don't size that heat pipe for that, size it for the design day, but don't measure it from a savings standpoint on that design day because you're spending such little time there. Focus on that shoulder day, use the valves to trim the unwintered heated design, capture as much free energy as you can the rest of the year. And last but not least, our Select Plus design software. If you haven't looked at it yet, I would urge you to do so. You don't have to download anything. Just go to heatpipe.com, click on the huge logo right in the middle, and all you got to do is create a user account. We'll send you an email, you do a password, and you're good to go. You can do bin analysis all yourself. Don't just take my word for it on all these numbers. Run them yourself. Plug in utility rates, locations, bin hours, all that good stuff, and see if the heat pipe is going to make sense for you on a job-by-job basis. Add valves. Again, call us. We're here for you. And finally, call me anytime. I'm available as needed, as are the rest of our application engineers and my counterpart out west. This webinar, first of all, I thank everyone here for joining. We're going to try to continue this wonderful world of heat pipe series. You're going to see some exit survey questions here. I asked if you have any warm things to say, even cold things to say, I can handle it. But any advice on future topics you want to cover, any questions that have been asked would be great. This whole webinar has been recorded and will be online for anyone to download, whether you want to save it for later or share it with any of your counterparts or customers. Please feel free to do so. And if you're looking for any PDH certificates, shoot me an email or us an email. It'll come to me, and I'll make sure that we get one specifically for you. With that said, I'm going to go to the question board here, and for those who want to stick around and see what kind of questions we had, love to have you. So first question, how reliable are those solenoid valves? How long do they typically last? Manufacturer, warranty, all that good stuff. Okay, so they are very reliable. I mean, we don't make solenoid valves. We get them from Sporlan. So it's a very common valve. I'm not going to say that they last forever, but they last a lot longer than the air handler does. The fact is the life of a solenoid valve is based on how often it opens and closes. And, you know, even if we're shutting down circuits at those peak days, it doesn't happen a whole lot. So the amount of times the solenoid valves are open and closed each year is very seldom. So they're going to last a long time. And worst case scenario, if you've got an air handler that's lasting, you know, 50 years, or you've replaced the pieces of the air handler while the valves are still there, the worst thing that happens is that spring goes bad and you don't have to take the valves off of the heat pipe. You can just open it up, take the spring out, put in a new spring, close it back up, and you're good to go. Warranty for the solenoid valves is 12 months. Next question, DOAS units should be sized for the AHRI max humidity conditions versus design air temps. This would mean outside air at 8278 versus 9578. How does this change your ratings and efficiencies? Well, I mean, it's gonna change it, but it's all gonna be relative. Whether it's 9578 or 8278, all the heat pipe is looking at is that 95 and the 82, so that's a 13 degree delta T difference. But either way, we're shredding sensible cooling from that DOAS unit's capacity. So it's, you know, if it's more humid air, it's going to have either more moisture removed or less efficiently removing that moisture. But either way, we're going to make it more efficient because we're handling that sensible load for it. I didn't run numbers at 95 versus 82 or anything, but I can tell you that no matter what those conditions are, as long as the heat pipe is on, whether we're talking EER or MRE, we're going to improve the efficiency. I can't tell you whether it's that 10% or 25%, but it will certainly improve it. All I know is that the MRE that's been standardized is based on 9578. But I do agree with whomever wrote this that since the focus is ventilation, air, and humidity control, that it should certainly look at that max dew point condition as well. And I would urge you as an engineer to certainly look at both conditions and see how the heat pipe aids that in both scenarios. Next question, can control valves be added to existing heat pipes? I'm looking at Maz here. Nobody can see me, but I'm looking at Maz because I've never seen it done. But Maz was born along with the heat pipe. They somehow came out of the same womb. It's crazy. Can it be done?
Actually, yes, but it's not very practical because more room is needed on the back end to house the valves. And typically, when we go in, you know, we take advantage of that space, and there's not a whole lot of room usually in the back to even have our connecting tubes, let alone valves. So it can be done theoretically, but it's on a case-by-case, I guess, on a case-by-case basis. Yes.
Thank you, Maz. Last question I have is, where does the airflow distribution within a school typically create imbalance in comfort as far as temperature and humidity is concerned in a decoupled system? Well, most times when I see schools and when it comes to a decoupled system, typically that decoupled outside air is being distributed directly to the classrooms, and then the classrooms either have like a fan coil unit handling the sensible load in the space, and typically that DOAS air is being provided at near neutral air conditions or maybe slightly colder to somewhat aid in that sensible cooling. But I haven't heard of the air distribution being a problem. And I mean, to me, air distribution from an air movement standpoint is a whole different animal than what the heat pipe's doing. So I'm probably not the expert when it comes to air movement and from a distribution standpoint. But I know it's been done all the time. So I'm sure there are ways that it goes bad, but I'm sure there are easy ways to fix it. I just don't know exactly the answer to that. So that I can certainly take a look into that and get back to whoever wrote that. So thank you. So let's see. So your cooling capacity savings is based on full load design days, but then you suggest reducing the heat pipe capacity on those days so the full load cooling savings is reduced. So what's the best sizing methodology for the cooling system? Well, you know, you kind of got two different animals here. You got what everybody wants to size it for, because you got to handle that worst case day, but then you've got the practical reasons of where you're spending most of your time. So you've got it, like all equipment, you have to size it to be able to handle the worst case day. But when it comes to efficiency, I would recommend selecting the equipment to be most efficient at where you're spending most of your time. So I'm going to go old school for me. I used to be a chiller guy. So to me, you always have to look at what's full load, kW per ton, or EER, because everybody, that's a common, a common set point everybody has to uphold to. But you spend so little time there that you actually want to size it to handle that best NPLV or that better part load performance. And to me, the heat pipes are the same way. You got to be able to size that heat pipe to give you the amount of coolant, pre-cooling for the cooling coil that's now sized at worst case, pre-cool for that worst case scenario, know what the reheat's going to do at that worst case scenario, but actually size the heat pipe. So if we're looking at savings, which is of course what we're looking at, look at that from a part load standpoint, since that's where you're going to spend most of your time. So that's how I would do it. I'd look at both, but from a savings standpoint, I'd concentrate on making sure you're optimizing your savings at that part load, since you're spending most of your time there. Last question. Beyond MRE, have you run any analysis of total yearly savings for zones that may have high needs for sensible cooling at many outside air conditions, such as interior zones? Does this change any recommendations? That is a good question, and I see it's by someone who is very familiar with MREs and DOAS equipment. Let me think about it for a second. I haven't run into any analysis. I mean, I can tell you that all the analysis that I've done here, I did myself. So I haven't run into any additional analysis, and MRE is fairly new to us. So I can tell you that our analysis and my analysis is going to be ongoing. So I haven't looked at it from a specific application to application standpoint. But it would make sense that the higher the sensible load or the higher the sensible heat ratio, the less a factor MRE is going to be, and probably the less need you have for a dedicated outside air system, honestly. But I don't think that's going to change the requirements as far as 920 and 90.1. But it certainly is going to be less of a focus if there's not as much of a latent load to be removed. But I still don't think that's going to affect, since we're sensible cooling anyway, it's going to affect the DOAS unit because it's handling all the latent load. But whether it's all sensible or all latent or a higher percentage of either, we're handling all sensible load in either case and just making life easier for the DOAS equipment. So I hope that answers your questions to some degree. Oh, and I do have one more. Does heat pipe have an alarm feature for any refrigerant leakage? No, we don't. The fact is, a single heat pipe is made up of many circuits, all individually closed and sealed circuits, so that if one, first of all, because there's no moving parts, it's not going to leak while in operation. The only times we hear of leaks is because someone dropped it in transit or hit it, or the controls guy, always the controls guy, right? The controls guy punctured it when installing a sensor or something like that. But once it's in operation, you're not going to have any leaks. But in the strange case where there is a leak, because we're talking one of many circuits, it's such a small amount of refrigerant that's leaking, I don't even know if there'd be an accurate means to detect it. So no, we don't have anything on there, but it's so small and so unlikely that it doesn't make a lot of sense. So that's all the questions I got. One question that is often asked, that's not on here, is why don't we see wraparound heat pipes in DOAS units all the time? Because believe me, I'm looking at this stuff, and obviously I'm biased, I will admit that, but to me it makes tons of sense to put a wraparound heat pipe on a 100% outside air unit. So why don't we see it all the time? And the fact is, most DOAS units are DX, and most DX DOAS units just don't have a lot of space for us to go wrap around a cooling coil, whether it's a filter rack butted up against the cooling coil, the hot gas reheat coil, flush mounted downstream of the cooling coil. We don't get a lot of space when it comes to DX equipment. With that said, we are starting to see more manufacturers, probably and not coincidentally because of this standard 920 coming around, that we are starting to see more and more manufacturers come to us and making modifications to their units to allow for us. Because again, now that MRE is going to be required and maintained, it's more important than ever to remove that moisture efficiently. So we're starting to see it more and more, and I think you as a customer, as an engineer, as a manufacturer are going to start to see more and more, and know that you know, whether you want, if we're talking manufacturers here, if it's something you want to install yourself, we can easily send you a prefabricated wraparound heat pipe that you can slip right in, or you can send your equipment to us and we'll install it for you, as long as we're given enough space both upstream and downstream of the cooling coil, plus some space around the U-bends of your cooling coil to do our connection piping. We can get it in there for you, then ship the completed unit to the job site. With that said, I appreciate, again, everybody's attendance here. I hope everyone enjoyed it. I appreciate any feedback you can give me on these exit survey questions. Emails are always appreciated. And again, if you're looking for some PDH certificates, shoot me or the company here an email, and I will take care of it for you. So thanks again, and have a wonderful day.